This instructional video is to give instruction on the yellow sheet, the half reaction sheet, and on how to combine half reactions. As you've previously seen in balancing redox reactions, you're required to calculate the oxidation numbers for each of the elements in the reaction, and then to figure out how many electrons are being transferred between the goat and the wolf. The yellow sheet separates the two reactions into oxidation reactions and reduction reactions and shows you what the electrons are doing, so whether or not the species is providing electrons or taking electrons. You'll notice this is different than any other reactions we've seen because there are electrons in the chemical reaction. That's why these are half reactions. In order for a reduction or an oxidation to take place, they must include the other one. That's why they're called redox reactions. So these reactions cannot happen on their own. They must be combined into one full reaction in order for there to be oxidation and reduction. Oxidation and reduction reactions happen simultaneously. So in order to have reduction, you must have oxidation. And the benefit of this is that it shows you how the electrons are moving. There's a lot of information on this sheet, so let's go over a few of the pieces of information that are important. On the left side of your sheet, you will see oxidation half reactions. The oxidation half reactions show a species that is being oxidized on the reactant side, so that'd be like F minus. And on the product side, it's showing what is produced from the oxidation of F minus. And F minus oxidizes into F2 and 2 electrons. So what this half reaction is showing us is that when 2 F minuses are oxidized, they produce 2 electrons. And we can see that is the case for all of our oxidation half reactions, that the electrons will appear on the product side of the reaction. This is because oxidation means to lose electrons. And so it's one of the products. It's a product of oxidation that you make electrons. So all of the oxidation half reactions will have the electrons on the product side. Generally, that means either starting with a neutral atom or a lower oxidation number. So many of the elements at the bottom are in their elemental solid metal state, because they have electrons to lose. On the right side are the reduction half reactions. And you'll see here on the reduction half reactions that the electrons appear on the reactant side of the chemical equation. To reduce means to gain electrons. So they appear on the reactant side because the reduced species is gaining the electrons to convert into a different species, the reduced form. So you'll see on this side that the electrons always appear on the reactant side. So that's the general format of our half reactions for oxidation and reduction. So we need to talk a little bit about what the other words on the page are showing us and some trends that we see. So this word here is a reducing agent. If I said I was using a cleaning agent, I would be cleaning something else with my cleaning agent. That's the same thing for a reducing agent. A reducing agent will provide electrons for something else. That actually makes the reducing agent the goat. If you're providing electrons, you're undergoing oxidation and reducing the other thing. So that's why they're called reducing agents, because it reduces something else. And to reduce something else, you must give it electrons. So these are reducing agents. These are all the reducing agents. These show up as reactants in our chemical equations. The opposite of that would be oxidizing agents. And oxidizing agents, as you can assume, take electrons from something else. That would make it a wolf, because it's taking electrons, so it's undergoing reduction. And that means it's oxidizing the other thing. Oxidizing agents will appear in the reactant side here because they are taking electrons from something else, meaning they are being reduced. So that's our reducing agents and our oxidizing agents. You'll see here on the side that our reducing agent gets stronger as you go down the list on the oxidizing side. So as you go down this way, the reducing agent becomes stronger. And stronger means that it will be more reactive. So we can see here, lithium is our most reactive metal. And this is why we don't find it in nature. It's highly unstable in this solid state. It's a very strong reducing agent, which means it's going to easily and readily give up its electron. And the same thing for the oxidizing agent, except for the oxidizing agent increases as it goes up. So the strongest oxidizing agents are at the top. So it's very favorable for F2 to become F-. Whereas at the bottom, we can see that lithium is our weakest oxidizing agent. It's very unfavorable for this lithium to regain its electron and become lithium solid because this is an unstable state of lithium. Therefore, it is a very weak oxidizing agent. The last thing on this page that is very important are the electrode potentials. Electrode potentials determine the strength of the oxidizing agent, and they can either be positive or negative. And you can see here that what's on the left side is inversed onto the right side. So these are the same, just reversed. And so you can also see that in the sign of the electrode potential. So the electrode potential tells us how favorable a reaction is, and that favorability that is determined by how positive the number is. So a very positive number is very favorable, and it's going to react. If it's very negative, that means it's very unfavorable, and it requires the input of energy to make this reaction happen. We can determine if redox reactions will happen by combining their electrode potentials and looking at that number. If the number is positive, that means the reaction will happen spontaneously. However, if it's negative, that means the reaction has to have the input of energy to make the reaction happen. Very large positives are highly favorable. They will happen quite readily. You can see this in the reactions of the alkali metal group. They react very readily. So sodium, potassium, lithium, if you drop them into water, they react and they burst into flames because it creates so much energy. It's a very downhill reaction going towards a product that is much more stable. Half reactions are important for a few reasons. Firstly, they allow us to see what the reactions are separately, and they allow us to see how the electrons are moving. Secondly, they allow us to combine reactions in order to determine if the redox reaction will happen spontaneously. And it will also help us determine what the products are of a redox reaction. Additionally, in combining half reactions, you will balance a redox reaction. So I'm going to show an example now how to combine and balance two half reactions. As you see here, reduction reactions cannot occur without oxidation, and vice versa. So the first thing that you need to do when you are combining two half reactions is make sure that you have one from the left side and one from the right side, so that you'll have an oxidation reaction and a reduction reaction. When a problem is asking you to combine half reactions, it'll give you the two reactants. The two reactants are going to either be the reducing agent or the oxidizing agent. If you have two reducing agents or two oxidizing agents, then you know that this reaction is not possible. You need to have a reducing agent and an oxidizing agent. Now let's look at how to combine half reactions, check our half reactions, and determine whether or not these reactions will happen spontaneously. For this example, I'm going to look at a reaction that you have seen in the lab before, but now we're just going to look at it from a new perspective. If you react aluminum solid with hydrogen ions, a reaction will proceed. The first thing that you'll want to do to combine these half reactions is to write down the half reactions. You'll need to find the half reactions that correspond to aluminum solid and H+ aqueous. It's important that when you're finding these reactions on your half reaction sheet that they each appear in the reactant side of the half reaction. Also, that you have an oxidizing, and a reducing reaction. So we're looking for aluminum solid, which we'll see here, aluminum solid. This is the oxidizing reaction. And over here, we have H+, which is the reducing reaction. So we're going to write down both of those reactions. And we'll want to line up the arrows of the reaction. So I'm going to start with my aluminum reaction. Aluminum solid produces aluminum 3+ aqueous. And this reaction produces 3 electrons. So now I have my aluminum reaction, and I'm going to write down the half reaction for H+. So that's 2H+ aqueous plus 2 electrons produces H2 gas. The next thing that you need to do is balance the electrons. Aluminum is our goat. And H2 gas, H+ ions are our wolf. 1 aluminum will produce 3 electrons. 2 H+'s require 2 electrons. If we were to combine these as is, we would have a leftover electron, and you can never have electrons left over in a balanced chemical equation. Therefore, we'll need to find something to multiply these by to increase the electrons until they're the same amount. We want to transfer the same amount of electrons from one to the other. So for every electron that is given up by the goat, must be taken in by the wolf. And so we'll need to multiply the aluminum reaction by 2. So I'll have 2 aluminum solids. That will produce 2 aluminum ions, as well as will produce 6 electrons. Because 1 aluminum produced 3 electrons, so 2 aluminums will produce 6 electrons. I have distributed this multiplier as the coefficient for all of my species here. And when you get to a coefficient that is not 1, like the aluminum was, then you multiply the multiplier by the coefficient. We'll need to do the same with the hydrogen reaction as well, because now I have 6 electrons that I'm transferring. This reaction as is only requires 2 electrons. Therefore, I'll have to multiply this by 3. And so if I multiply it by 3, I'll have 6 H+'s, 6 electrons, and 3 H2 gases. Now I have the same amount of electrons that are being transferred. And when we combine our reactions together, we will eliminate the electrons from the reaction. So that is what's going to happen next. So I'm going to cancel out my electrons. These have been transferred. My 6 electrons have been transferred to my hydrogens, so those no longer appear. Now we'll need to combine our equations into one large equation by combining the reactants on one side and the products on the other. So it doesn't matter which order you do this in, one reaction or another, just as long as all of the parts are there. So the first thing I'm going to pull down is my 2 aluminum. So I'm going to pull that down here and write it down. 2Al solid. I am also adding in the reactants 6H+ aqueous. So that came from here. this reaction produces 2 aluminum 3 pluses, which I'm getting from here. Pull that down. 2 aluminum 3 plus aqueous and 3 H2 gases. So this would be our final balanced reaction. We can check to make sure that we balance this correctly with the total charges. So we'll start on the reactant side. Aluminum is a solid, so its charge is 0. H plus has a charge of +1, and we have 6 of them, so it's +6. So the total charge on our reactant side is +6. If we balance these correctly, then the total charge on the product side should also be +6. Aluminum 3 plus has a 3 plus charge, and I have 2 of them, so that's +6. And hydrogen gas is 0, so combined that's +6. So I have balanced this correctly. When you're combining half reactions, you'll also want to check and see if this reaction happens spontaneously, if it's energetically favorable, or if it's energetically unfavorable and will not happen spontaneously. If that's the case, then you have to input energy to make the reaction happen. You should already know that this reaction is spontaneous. As you've seen in the alien blood lab, when you put acid onto aluminum, it will produce H2 gas and it will disintegrate, so to speak, the aluminum foil. So we can check to see if that's true with the electrode potentials. So we go back to our half reaction, and we see the electrode potential of aluminum is plus 1.66. You'll notice that I did not multiply it by my multiplier up at the top. Do not multiply it by anything. It's an intrinsic value, so it doesn't change with amount. So do not multiply electrode potential by multiplier. Leave it as it is. My electrode potential for hydrogen is 0. So we add those together, and the total electrode potential for this balanced chemical reaction is plus 1.66 volts. That's a positive number, so this reaction is spontaneous. It's energetically favorable, and so this reaction will proceed. You have also tried other reactions with H+. For instance, if we mix together H+ and copper metal. You may be able to tell from the activity series that hydrogen is not strong enough to steal electrons from copper, which is true. So this is a reaction that we do not see proceed. But we can also show with the electrode potentials that this reaction is not spontaneous. The electrode potential for hydrogen, as we know, is 0 volts. And let's look at the electrode potential for copper, negative 0.34. And if we add these two together, we'll get a total electrode potential of negative 0.34. This is negative. That means that this is not spontaneous. This reaction would require the input of energy to make it happen. So that's a way that you can look at these electrode potentials and tell whether or not a reaction will proceed. This tells you if reactions are favorable or unfavorable, and if they'll happen spontaneously. So that's some short instruction on how to do our combining half reactions.